Excellent. Right. Thank you, Dan. So, yeah, I'm an assistant professor in quantum technologies, which is, to me at least, one of the most exciting areas of physics right now. So, a brief outline of my talk is, broadly speaking, who, what, where, why, how. And firstly, in terms of who, as scientists, as an academic, I just want to, I'm delighted to be invited to come and give this talk. And I just want to really emphasize science communication as a scientist is at the heart of pretty much everything we do. The only useful science research is science research that people read, that people hear about, that people can use, and people can apply to their lives. And that comes in via teaching students, who ultimately may go and do useful science things. This comes through preparing papers. And this comes to giving talks, be them at conferences or to the public. And given that the public funds a huge amount of science research, and it's really exciting, then it's really important that you guys hear about what it is we do. So firstly, what is quantum? I will probably say it about 80 times during this talk, so we might as well have a good idea what it means. Are there any volunteers for what quantum might mean? I mean, you've all signed up to come. Yep. Really, really, really tiny? Yep, it can. Yep. Discrete, excellent. So something in like discrete little bits, itemized. Yep.
Something on like a molecular?
Yeah, on the molecular or atomic or some other tiny, tiny length scale. Exactly. And obviously what I should do, obviously, is ask ChatGPT, and it spits out some answer about often the smallest possible unit of something. This might be the smallest possible unit of light, of energy, of current, be that like a single electron, it might be a single atom, a single particle, a single piece of spin. That's broadly what quantum is. And then from quantum, so quantum recently, last year, celebrated its 100th birthday. And from that, we're now entering this era, if you like, of quantum technologies. And broadly speaking, many quantum technologies can be grouped into roughly one of three categories: quantum sensing, quantum computing, and quantum communication. Okay? And the sensing one, maybe that's the most intuitive. Whenever we have these little bits of something, these discrete units of energy, they're inherently incredibly sensitive. Often it's very, very hard to measure them, but they are incredibly sensitive. And so if we can get these quantum particles to a regime where we can measure them, then the sensitivity they can detect is incredibly high. Slightly more abstract are the quantum computing and quantum communication ones. Okay, and the purpose of today's talk is to, broadly speaking, try and give you a flavor of why quantum. Why do the properties that are described in quantum mechanics give us an advantage in things like computation? And how can we leverage them to perhaps send codes or cryptography that are not encoded by how hard it is to solve a math problem, but instead by fundamental laws of physics. Okay? And the two main properties people will mainly hear when we talk about what quantum properties are we going to do? What's the quantumness? Superposition and entanglement. So hands up if you've heard of Schrodinger's cat. Okay, excellent. So for like the one or two people who didn't put their hand up, but probably have. Schrodinger's cat was a thought experiment nearly 100 years ago, mocking quantum mechanics. And this will be a recurring theme, because a lot of quantum mechanics is, from the outlook, absurd. Okay? And when Schrödinger was saying this, he said, oh, quantum mechanics is so ridiculous, it says that if I prepared a cat in a special way with some nuclear isotope that's decaying, that would hit a hammer to break some poison, that might kill a cat, quantum mechanics would say the cat is dead and alive at the same time. And that's just silly. As it happens, to some very crude approximations, that's exactly what happens. Okay? They're very hard to make. Things that are macroscopic, things that are real life, and we can see and touch and pet, preferably the alive cats, but they're very hard to make. But in principle, that's what quantum mechanics says. This second one is a little bit fuzzier, okay? The idea of entanglement, okay? At its heart, all entanglement means is correlation, okay? Two things are correlated. If you ask them the same question, they'll give the same answer. And, you can imagine, and this gets bundled around a lot with things like quantum teleportation, faster than light information, all of this kind of thing. And what makes it special, if you like, we can take a very normal, regular example of I have two gloves, and I put them in two separate boxes, and I give one to my friend, and they fly halfway around the world, and they open their box. And they see it's a right-handed glove. Okay? They see it's a right-handed glove. They know instantly, faster than light, if you like, they know instantly that my glove is left-handed. Okay? Nothing weird, nothing magical there. The difference is, from the point of when they took their box, there was no way they could ever get anything other than a right-handed glove. That's what was in the box. And so for entanglement to work, and for entanglement to be special and useful, it's got to be twinned with superposition. It's got to be twinned with the idea that opening the box, and you might ask, well, what color is the glove? And they're going to be the same color. But it has to be that there was some chance, some quantum chance of it being different. And that when you open the box and you perform a measurement, you look at it, you decide the outcome at that moment. And what becomes spooky is if we open those two boxes and we're half a world away, they will always agree if they've been entangled. Okay? And that's the real kind of magic of it. Now, as I said, quantum's about 100 years old. Now, back then there was just quantum mechanics. Now, I prepared a very exciting word cloud of the top hits on Google of what comes after the word quantum. And there's a lot. And this is incredibly well surmised in Ant-Man, if anyone's seen it. Do we just put the word quantum in front of everything? And the answer is pretty much yes. Quite a lot of people, myself included, spend quite a lot of time trying to think about how we can exploit those ideas of superposition and entanglement to do things better than we currently can, or to do things that support what we currently can. Building a quantum computer is not about replacing your desktop. It's about understanding what problems computers find hard, and that quantum mechanics and quantum computing algorithms can support better, and have strategies to do those bits. Okay. And to kind of illustrate this, I've got two math problems on the board. Okay. Now I can hear the audible gasp. I'm not going to ask you guys to do math, okay? That's not really the point here. And on their surface, I'm sure many of you are tapping away at your calculators that you brought with you. At the surface, they look like very similar problems. Okay? They're both, broadly speaking, multiplication problems. But one of them is a lot harder than the other. Hands up who thinks A times B is harder? Yeah, okay. Anyone for 47 times 53? I imagine someone solved it by now. But not all problems are created equally. And in fact, the A times B, it's probably something like, 19 times 21, something like this, right? Which you can check. You can verify it very easily. But what I'm asking you to do on the left is prime factorization at its heart. I've taken a large number, 3 digits, ooh, scary, and asked you to factorize it. And that's hard. And I say it's good that that's hard. That's the foundation of a lot of encryption right now, okay? The fact that computers, and broadly speaking, as humans, some kind of functional brain, we are doing these kind of computations. Computers find that a hard problem to do, okay? Whereas the one on the right, okay, slightly bigger numbers, but not too difficult. Some of you will have learned long multiplication. Some of you will have had a calculator on your phone. And it's very straightforward. Okay, so the point here is not all problems, even if they look very similar, are created equally. And to illustrate this even more, on your desk, some of you, most of you, will have a sheet of blank paper. In a minute, I will ask you to turn it over. And what I want you to do is put your hand up when you find the word quantum on your list. Okay? Right, go. So we have some people very quickly. Some people will be taking a bit longer. Excellent work in the front row. Okay. Right. All right. I think most people have found it. And what I'd like you to do is, if you've got a neighbor, look at their sheet, or look at someone's sheet next to you, and tell me if you think it was a fair competition. Right. Hands up who thinks that was fair. Hands up who thinks I rigged it. Now, this can be quite funny if I made you stand up and there's one person sat down, one person stood up. And some members of the audience, not all, will remember this archaic piece of history, a phone book, okay? So back before the internet, when people still had to call things on landlines, there were these devices called phone books. And they would list phone numbers. And they would normally be sorted alphabetically. So if you wanted to find me, you go under H, and if I hadn't ticked the box to be unlisted, I'd be there. Wonderful. If I gave you a phone number and told you to find it in the phone book, that is very hard. Computers find that very hard. Broadly speaking, computers don't have a good way to find it. They put all the numbers in the list and they go looking. And roughly, you can show with some fun math, encourage you to try it at home, that on average, it will take n over 2, where n is the length of the phone book. Okay. An even more fun fact, that in Jersey, back when they had phone books, they would duplicate the phone book, one in alphabetical order and one in numerical order, just because of how small Jersey was, where this example wouldn't work as well. Okay. So this kind of operation, this search, is actually one of the things that has been shown if we could build a quantum computer, then this is one of the things we could speed up. Okay? And finding a specific entry in a huge amount of data is probably quite a useful thing. Another one of the sort of algorithms that has been shown to be sped up by quantum is actually that prime factorization. And so you might imagine why lots of governments are pouring lots of money into quantum computing with the ability to factorize large numbers into their primes when 90% of encryption is currently based on that. So now to drive home why or how quantum starts to give us this advantage. And so we spoke about superposition, and we can imagine some kind of coin with 0 or 1 or a bit, or however you want to describe it. And we put it in this sort of 50-50 state. And I lied, there is more math. If we have a little bit more math, and we take this bracket, 0 plus 1, and we raise it to the power 100, so we have 100 of them, and we kind of go around and we expand the brackets, as some of you will have done in high school. And it turns out that the number of different brackets you would get, so your first one is just all zeros, and then the second one is all zeros with a 1 at the end. And this goes on until you get all 1s. And it turns out if you have just 100 of these, just 100 of these bits, quantum bits, called qubits, if you have 100 of them, the number of different possible states that you have is about 2 to the 30. Oh, no, sorry, 1.2 times 10 to the power 30, 2 to the 100. Okay, now, obviously that looks like a big number. It is a big number. But this is made of just 100 quantas. Might be 100 atoms, might be 100 photons, might be 100 spins, wherever they are. And okay, but how big a number is this? With just 100 of these. The number of seconds since the Big Bang, 13-something billion years ago, 1 times 10 to the power 21. So if you tried labeling or reciting or itemizing all of those different elements from that sort of bracket expansion, and you were doing that one every nanosecond, 1 billion times every second, you would have had to have started counting at the dawn of the universe. Just 100 atoms. People are now putting sort of quantum computing arrays of up to about 1,000, maybe 6,000, I think there was a paper last week on. that there are more states to be labeled, more possibilities, if you like, and I'll get to possibilities in a minute, than there are atoms in the universe. Okay? And I could say very cheesy things, like, quantum computers follow all of these paths simultaneously. And there is some truth to bits of that. And that's an analogy I will abuse a lot later. But just the sheer volume of the number of states that you can access via this sort of fundamental principle of quantum mechanics is truly staggering. So, how to make you guys sort of visualize the way in which this sort of manifests on a quantum computer. So, hands up if you've played Snakes and Ladders. Excellent, okay. Some of you will have played it online or on a phone. Some of you will have had actual board games with dice. And there's some credit here to Nick Berry and John Burkett, who have done some very nice sort of quantum simulation, or not quantum simulation, Snakes and Ladders simulations. And so I've got a sort of made-up board on the left there. And can someone give me an example of somewhere I'd be after one roll of a dice? Yep. Square number 3. Excellent. Okay, not a trick question. Any more? Where else could I be? Yep. Square 4. Sort of. But actually, if I rolled a 4, I could have rolled a 4. I should probably have said those yellow things are ladders. And so you'd actually end up on 14 or whatever. Any others? Yep. 38. After one roll of the dice? Yes. Okay. And we can play this game all day, but we probably get on with the talk. And broadly speaking, if I wanted to make a pretty picture, that is all of the places I could be after one roll. Okay? And we can imagine, and this is a tool to help you visualize how this kind of scaling in quantum mechanics arises from. After one roll of the dice, after one roll of my quantum dice, I'm somehow spread out on those 6 squares. So where will I be after 2 rolls? And on each of these, I've got about a 6th probability. Okay? Quantum mechanics has a lot of probability in it. Okay? There's some 50-50 chance of the cat being alive and dead. Some 1/6 chance on being on each of these squares after I roll my quantum dice. After 2 rolls, well, each of those 6 squares then opened 6 new possibilities for where I could be after 2 rolls of the dice. Some squares are more likely than others. They're a bit darker. You can kind of see on the, if you map out where you might go after 2 rolls, you can see I could have rolled a 1, got to 38, and gone any of the 6 squares onwards from that. Some squares I can't be on. I can't be on square 2. If I roll a 1 and then a 1 again, I'd be on 39. If I rolled a 2, I have to roll something next, and then get off the 2. After 3 rolls, I have followed 216 different paths. 6 cubed, for anyone checking my math. 216 different paths along the board in just 3 rolls of the dice. But I probably wouldn't have got anywhere near 100 yet. Okay? Be quite a boring game of snakes and ladders if you could win in 3 rolls. But 216 different paths that I've followed. And this is exactly this kind of principle is exactly how these quantum algorithms operate. They put some kind of like target square that you aim to get to. And you follow, in a way, you follow different probabilities, different amplitudes to try and get there. And you manipulate quantum gates, you do operations between squares to try and get there. After 10 rolls, which isn't a particularly long game of snakes and ladders, after 10 rolls, you can see, depending on how well it shows up on the projection, we're quite well spread out along the board. Okay? 10 rolls, 6 to the power 10, about 60 million different paths in just 10 rolls of the dice. Now, I say obviously all of this is just classical. There you go. And there's a pretty video of it going. It will probably go up to like 100 or something. So, and obviously there's probabilities that you get stuck in like a nearly endless loop. Okay? But after 35 rolls of the dice, you've probably lost the will to live and are sick of playing snakes and ladders. But there might be some finite chance that you haven't finished yet. Okay? But the likelihood is 99%, 99.999% by the time we got to roll 70, that will be at square 100. And it's this sort of, it's this kind of probability addition of these probabilistic events that gives quantum computing part of its power. Okay? Now, I'm going to move away from snakes and ladders in a moment and onto more dice games. But there's just a small shout out to highlight. There's a wonderful society called Girls in Quantum, and one of our UOB students, undergraduates, is currently helping me turn this idea of quantum snakes and ladders into a sort of demo that people can access online and play around with. I encourage you, Girls in Quantum, it's a fantastic organization. I'm very proud to be on the advisory board of it. And as I say, one of our undergraduates currently working with me to make a sort of web applet demo about this. So, on to my research. The real reason you all came here today. Oh, serious. Photons, okay? So, anyone know what a photon is? Yeah? A quantum of light. When we take light, it might be coming from a light bulb or something, and we take light and we filter it down and down and down. And eventually we find that, for hundreds of years we thought light was a wave, and sometimes it is a wave. Okay, I won't talk too much about wave-particle duality. That's a whole nother cat in the box I don't want to open. But, hundreds of years we thought it was a wave, and then eventually some clever guy called Einstein proved that light could be treated like a particle, sometimes. And this is broadly what my research is on. And photons occupy not only a special place in my heart, but a special useful place. They are pretty much one of the only things that can exist and be quantum at room temperature. Many of you guys will have heard of, you will have seen on the news things about quantum computers, and many of them will be things like superconductors, which have to be bathed in liquid helium. They might be atoms or ions cooled with lasers. They might be little electrons trapped in diamond, again, bathed in liquid helium. They might be a quantum dot, whatever that is, but again, put in a cryostat. Photons are truly one of the only things that, at room temperature, remain quantum. And broadly speaking, why this is, it comes down to energy. Okay, when we have all of those superconducting circuits and things, the energy of them, as we heard at the beginning, the energy of them, lots of people said quantum's very small. The energy scales are very small. And this is true. And this means when we're at room temperature, and we're bathing in infrared radiation, which is just heat, that energy will be added to these tiny quantum systems and completely wash it out. But with photons, if you use the right photon, it's well above room temperature. Okay? And it can exist and not be affected by this noise. And my research is slightly broader than just photons. And the key part of it is how to store a photon and why you want to store a photon. Okay? So, as to why you want to store a photon, photons are very quick. Okay? That is probably an understatement. Getting photons to be at the right place at the right time is very, very hard. Okay? Trying to synchronize 2 photons, 4 photons, 5 photons to all appear at the right time is very, very hard. Add in the effect of this probabilistic effects, really, really hard. So that's where quantum memory is, which is broadly speaking one of my areas of research. And these can be used anywhere from sort of local networks that you might find inside a quantum computer or a quantum data center. I say I haven't made the quantum data center up. It probably exists, or if it doesn't, it will soon. These might be links between buildings, between cities, across continents. If you're going to send quantum information, if you're going to share quantumness of entanglement and superposition, and you might want to do that for sending encrypted messages. You might want to do that to host a cloud quantum computer. You're going to need to send information that is quantum. You're going to need to send information where you can't open the box and look at it. And photons are pretty much the only way you can do that. And so being able to send them, store them, becomes very important. And to kind of illustrate this, here is a type of quantum computer. I won't talk about the details of it too much. Broadly speaking, this is a bit like a microchip for photons. And what you do is on the left-hand side, you put photons in, and at each of these intersections, the photon has a choice. Okay? And it splits in half. But remember, at the beginning, we said quantum meant single individual units. Okay? So it can't split in half. It has to make a choice. It has to go left or right. Or it has to go left and right at the same time and follow the superposition. Okay? And these paths, like on the snakes and ladders board, they all spread out. Maybe they all come back together and they interfere. Unfortunately, something probabilistic happens every time. Okay? So can I get a volunteer or a victim? I'm not fast which. Yeah, there. Yeah. Now we're talking. Okay. Hello. Right. So, what's your name?
Laura.
Laura. Right. So, your job, and you're going to have a really fun job whilst I talk. At each intersection, something probabilistic happens. Okay? So what I'd like you to do is take those 3 dice, and I'm going to keep talking, and roll, each time, roll the 3 of them, and get 3 sixes for me. Okay? And then align them so people can see your victory. Okay? And whilst Laura is playing dice games, this might make some of you think of Yahtzee. Now, I'm not expecting as good a turnout as for Snakes and Ladders, but hands up who's played or has heard of Yahtzee. Okay, better than I was expecting. So, in this modified game of Yahtzee that Laura is playing, where I've asked her to get 3 sixes, and she's got one, and another one, and you try to create certain combinations. And, we're close with 2 sixes and a 5. Okay, and what Laura's kind of done, thank you very much.
Oh, 3 sixes?
Yes. Oh, wonderful. Okay, great. Maybe if the technology works. Wonderful, okay. So, almost against the odds, about 1 in 8,000, Laura managed to get 3 sixes. Say I wanted 5 sixes, as you do in the game of Yahtzee. That becomes even more unlikely. Okay, I think, so, but what if we could store the successful outcomes? What if, when I roll a 6, I could keep it and just roll the other 2 dice? And then when I get another 6, I keep it and I roll another 2 dice. And suddenly, we've gone from trying to roll 5 sixes, about 1 in 8,000, to the ability of storing a successful outcome where it's safe, we don't look at it, it's not zooming out at 300 million miles an hour, and then we can synchronize it with other successful outcomes. And that's the underlying principle behind a quantum memory. And these probabilistic operations, these might be entangling things. How do I take 2 photons, smush them together, and then send them to other ends of the universe, such that I get those correlations? And being able to synchronize and save those successful operations is incredibly powerful. So, just for the die-hard atomic physicists in the room, which may only be me, but how do we do that? Okay, how do we store an atom? How do we store a photon? And the trick is, you might have guessed by the atomic physics bit, we use atoms. There are lots and lots of different ways to store photons. This is one of them. This is one of my favorite ones. Be nice to it. And atoms are very good. They have energy levels. Energy levels can absorb photons. Wonderful. Not wonderful. You excite an electron in an atom, and it'll fall back down. And your quantum state is lost. So what we do is we take a single photon, that's the line in red, and at the same time, with a bunch of atoms, we go to a high energy level, and then with a big laser, we push it back down, and it goes into kind of like a storage state. Okay? So it goes into some kind of storage state. And what that means is it's safe. That photon is safe. It's now in this dark storage state. For technical reasons, we call it a spin wave, because it's done in lots and lots of atoms, and these are the spins of the atoms. And then, when we want our photon again, we turn our big laser back on, and as if by magic or atomic physics, they are mostly indistinguishable, turn the big laser back on, and our single photon comes spitting back out. Completely unchanged, completely unmeasured, the cat is still alive and dead. And you can go one step further. We can put those atoms on satellites. We have PPS, is some probability pair source, so that's making entangled photons. And broadly speaking, in the middle, you measure 2 entangled photons, store the other half in some quantum memories on a satellite, and at the end of the day, do a couple more measurements, you end up with photons or satellites that are entangled a long way away. And this is the underlying principle of how we'd make one version of a quantum internet, where we want to send quantum information, we want to send entanglement across the world. So I'm probably nearly running out of time. So I've talked about sensing, I've talked a little bit about computing. I've not talked too much about quantum communication beyond supporting quantum computing. Just so nobody panics too much, when I said quantum computers can factorize large prime numbers, at one point within the past 4 or 5 years, that record of the largest number that was factorized by a living quantum computer was 21. Okay? 7 and 3, for anyone still struggling with prime factorization. The prime numbers that we'd be talking about would be hundreds of digits long. So there's still quite a long way to go. And then part of the job of scientists is to say, okay, well, if we do want to send secure communication, which governments probably think are very important, then can we do that in ways that is guaranteed by the laws of physics? And the short answer is using things like quantum memories, sending things like photons in superpositions, those alive and dead cats. We could tell if someone peeked at it halfway. We could tell if someone opened the box, because these quantum states are so fragile that if someone opens the box, if they look at it, if they measure it, if they try to gain any information out of it, it ruins it, and you can detect that. And so we have methodologies to send information secured not by my very big computer can factorize prime numbers, but secured by how we currently understand the laws of physics. So, at least in my opinion, quantum technologies, they're very, very cool. As hopefully the sort of factorizing 21 has shown, we are a long way away from many of these sort of promised applications. But the applications and the friends we make along the way are all going to be very exciting. And it's a really interesting place to work. It's really interesting research to do. And I will always be very happy to wax lyrical about quantum mechanics and quantum technologies. So if you've got any questions, now would be a good time.